tired. Okay. Can everybody hear me? Can you hear me? And if you can hear me, you should be able to give me a thumbs up or something, right? No? Okay. Wait a minute. If somebody asks me a question, where am I supposed to go? Okay. If somebody send me a chat or something. Chat, yeah. Okay. Oh, got it. Click the icon. And if they have any question. Okay. All right. Okay. Good. I bet everybody is so tired by now and want to get out of the class ASAP, and we can do that. But I'm getting paid, so I have to talk something, right? Yeah. My name is Hiro Kobayashi. Okay. All right. Actually, it's Hirohito Kobayashi. Okay. All right. Hirohito, Hirohito, and Kobayashi is the last name. But Hirohito is very long name, and it's very hard for Americans to pronounce. So when I was in US, I asked them to call me Hiro, Hiro, and and sounds like Hero. That's even better, right? So that's me. So you can just call me Hiro or Kobayashi-san. That's fine. And I am half Taiwanese actually. I'm half Taiwanese and half Japanese. Okay. All right. And I was hoping to get to know everybody. Only we have 5%. How many students we have? It says 15 here, 5 here, so total is 20. Student? 18. Okay. All right. Then I would like to get the mugshot sometime. But anyway, short introduction of myself. I grew up in Japan most of my life, and I went to Waseda University, 早田大学, and originally I wanted to be an architect, 建筑师, okay, and I wanted to be a designer, okay, and but after first semester, my advisor called me and say, okay, he told me a cold fact. He said, your design really suck, very bad. So he said, there is no future for you as a designer. So he kindly invited me to be a structural engineer. So after that, I became a structural engineer, earthquake engineer. And after graduation, I got a job as a structural engineer in Japan. A couple of years later, I thought, maybe I should do a PhD. So I moved to UW-Madison. Then I studied about the wave propagation and application of wave propagation to medical ultrasound. So that's my background. Okay, all right. And I'm with the manufacturing process group at the NTUST. Yeah. So I decided to, my wife is Taiwanese, and we decided to come back to Taiwan 2 years ago, roughly 2 years ago during COVID. And so I started looking for teaching position, and I found the advertisement of NTUST. And only between here, I cannot tell this out loud. I thought I was applying to National Taipei University, Taipei Gongzuan, because that one is very close to my father's house. So I thought, oh, okay, this is great. And I applied, and Lin Lao Su from NTUST contacted me, and we had the interview. And just through the interview, I found out, oh, okay, I was not applying to Beiketa. Actually, I was applying to Taiketa. And fortunately, I ended up here. Yeah, so that's me. All right, so anyway, my task is go through the review of the strengths of material, okay, which all of you should know by now, right? Right, 材料力学, okay, good. But it's nice to review, right? So that's my duty, to review it. And end of the lecture, today's lecture, I have a small homework for you. Good. Any questions so far? Okay. Are you guys happy? Anybody? Hey, everybody on the line too. Are you guys happy with your life? How many of you are not happy with your life? Give me the thumbs up. So everybody's happy. Good. All right. Well, if you're not happy, I cannot do anything because you're adult, right? Right? Whether you're happy or not, that's your responsibility, not my responsibility. That's not your mother's responsibility, not father's responsibility. So, okay. All right. But, if you're not happy, think this way. It's Friday afternoon, 3 p.m., 4 p.m. It's done. You can go home or go somewhere and have fun. Good. All right. So here we go. Review of the strengths of material by Hiro Kobayashi. Okay. All right. All right. Chatting. Good. All right. Good. Okay. So, we at the end of this course, we are supposed to design a soft robot, right? Like a snake-like robot. Okay. And then one question should come to your mind. Why do we have to review the strengths of material? And strengths of material, 材料力学 basically covers elasticity, 弹性力学 viscoelasticity is 粘性弹性力学 I don't know. I can say this in Japanese, but I don't know in Mandarin. Okay, basically, actually it's relevant. Okay, so today I would like to talk about reviewing the statics and dynamics, and so that you find out actually later we need to have the knowledge of strengths of material to design soft robot, more or less. Okay, so today's part is more like a review of the statics and dynamics. Good. All right. Okay. Here we go. Statics and dynamics. Good. And here's the video. Can I see it? Can I think to? Oh, okay. Here we go. I found this website talking about the wall climbing robot. Can I play this? Okay. This is not exactly a soft robot we are thinking about, but part of this wall climbing robot is actually soft, right? Here's a robot sticking to the wall and gliding up. Good. This part is hard structure, but you can see this belt is sticky and soft. So this part, definitely we can treat this belt part as a caterpillar part as the soft robot. Good. All right. So basically, I will use this to talk about review the statics and dynamics. And at the end, I hope I can convince you why we need to know the knowledge of the strengths of material. Good. All right. Okay. So here we go. This is the wall climbing robot, okay, created by Simon Fraser, is a university in Canada. Okay, so what we know is this wall is vertical. Okay. All right. What else do we know? What else do we know? What do we need to tell me? What do we know about this robot? There is a wall, and the robot is moving to the sideway, down or up, right? Moving up. Good. Okay. So something is moving, then that means I should be able to measure the acceleration and then later velocity, right? Good. All right. And what else do we know? What else do we know? Okay. Here we go. Okay. We have a caterpillar. As I said, this part is definitely rigid, but caterpillar part is soft and viscous, sticky. Sticky material usually is viscoelastic. Okay, right? Are we okay? All right. Then another part is, okay, this structure has a weight. Okay, each part we can break this down into this caterpillar part, 1, 2, 3, 4. And center, we have 2 links. Okay, very crude, but we can build this as a 1, 2, 3, 4, 5, 6 parts, right? Then another fact is we can simplify the weight of this caterpillar driving system is at the center here. Good, right? And also we see a link, right? Okay, weight of the link. Okay, of course, this is distributed. Okay, if you want to model this as a distributed loading, that's fine too. But I think this is at the first step of design. I think it's okay to build this as a one mass, okay, and concentrated at the center. So these are the weight of the links. Good. Okay. All right. And there is another cable. Clearly, we can make a battery-powered system too, but this system had a cable. So if this robot slides up more, this cable will start pulling down, right? So tension force. Good. Okay. All right. Then this is the basic specification of this specific robot. Okay. All right. Then what do we need to do after this? Okay, if you're a mechanical engineer, or of course you're all mechanical engineer, okay, what do we need to do after these specifications are given? What do we usually do? What teacher told you to do when you were a freshman or sophomore? I don't know, when you took the statics and dynamics. When did you take the statics? 经济学. When did you take it? 10 years ago? Or 100 years ago? Or because you look like you completely forgot the statics. When? 2 years ago? 3 years ago? 2 years ago. Okay. Oh, sorry. Maybe I should assume all of you are mechanical engineer. Some of you are material science engineer. Oh, sorry about that. Okay. All right. That's good. Then even better. We should go through this review. Okay, so basically these are the simple specification, right? Super simplified. Okay, then next step is, oh, sorry, I completely forgot the friction. Okay, friction is, surprisingly enough, friction will act under this belt. Okay, and friction is the one, because think about it, these weights are all going down, right? Right? Correct? But this robot itself is moving forward. That means some kind of force must be pushing this system upwards, right? Right? If we didn't have this, our answer should be this robot is going to slide down, but that's not true. It's sliding up. This is the fact. Also, another fact, we have so many forces are going down. That means we need some kind of force to push this system up, right? Okay, in this case, the friction happening between this surface and this sticky belt is the driving force to push this system up. Make sense? Right? We have one caterpillar here, another one here. So I couldn't sketch it, but we have one arrow here, one arrow here. I should put another arrow and here underneath 2 caterpillars. Good? Any questions, any concerns? Good, okay, all right. So specifications are given. Then usually in mechanical engineering, we have to draw a diagram called free body diagram, okay? All right, free body diagram, the idea of the free body diagram, pretty much like this, but we can build this from the side way, okay? The idea of the free body diagram is basically the structure with all the force information and the acceleration information, or I should say inertial force information should be put on here. Okay, then that's called free body diagram. Of course, if you want to get a more detailed picture, you can do so. You can remove this out, remove this link out, remove this link out, and you can draw 1, 2, 3, 4, 4 free body diagram, we can do so too. Okay, but in this case, we only interested in the movement of the entire system that way. So I think this is okay. Good. All right. So the next step is, this was the sort of the big picture. We have to somehow put this picture onto here. Good. And that is called free body diagram. Okay. Okay. And by the way, total mass is 4 mass of the caterpillar. C represent the caterpillar. I have 4 of them. Link is 2, mass of link, 2 of them. So the total mass is this. Of course, this is super simplified. Then this whole thing is going to, I'm assuming it's going to accelerate. So mass times acceleration is inertia, right? Good? All right. Okay, so here we go, free body diagram. Okay, we have to put all the forces we saw. Okay, all right. Okay, suddenly this came up here. Okay, the reason is, okay, since this link is, if we build this as a center line here, this link is away from the center line. Good. Let's say this distance is h of half. Okay. Then what will these weight will do? What are they going to do? That's right, because it's away. So it will try to rotate this entire system to rotate this way, right? Right? Okay, but we don't want the system to rotate, and the system was not rotating. Then that means we need to have another force to counteract that rotation. Okay, again, this is super simplified model. What we can do is put the reaction force here, right? And fortunately, this caterpillar has width. Let's say if this is D, this can be viewed as 1/2 of the D, right? Good. Then, great. Hopefully, these two will create the moment of the system rotate this way. Then with this existence of this will push this system with respect to this ring, try to rotate back. Good? All right. So this is the super simplified free body diagram. Okay. Any questions? Good. Okay. All right. Then free body diagram is done. Then usually what do we do after this? What do we do? I know I'm asking the question to all of you who are mechanical engineer. What do? We finished a nice, beautiful sketch. It's not so artistic, but it's nicely done. What do we do? Actually, this is the hardest part, usually. Usually this is the hardest part. Okay, the free body diagram is done. What's next? Anybody? Next step. This is already simplified. So, you know, we are engineer. Usually we would like to set up some kind of equation, no? And this is moving. I'm still assuming it's moving. So what do we do? Using this information, what kind of equation should we set up? Anybody? Remember? Something equation. Equation of something. Duty of an engineer, actually most engineers, is setting up the equation as a model, okay? Then we can predict the simplified version of the motion. That's the idea, okay? When I was an undergrad student, going through this was hell. Setting up equation was hell. I only felt like a teacher was trying to torture me, okay? All right, and I know some of you may feel that way, but actually once you become an engineer, you'll find out actually these simplifications are necessary, and setting up equation after this is very important as a first step of designing. Good. So using this, usually we will set up a, oh, sorry, I forgot the friction. Okay. By the way, okay, this one is a friction applying on this belt. Okay, so this is the one pushing this caterpillar. Okay, but there is we have to come up with an action reaction force between this caterpillar and wall, and action reaction force should cancel each other. So on the wall side, this friction force will point downward. Good. Okay, then this and this cancels each other, this and this cancels each other. Good. All right. But for us, what do we need to know? We can ignore this guy. Okay, has nothing to do with our to set up the equation of motion. Okay, so next step is setting up the equation of motion. Good. Okay. All right, we have X direction, Y direction. Okay, and this is basically moving up. So do you think we can set up equation of motion or some kind of equation in X direction? How do you think? Is this thing moving in that direction? Is it? Is this thing is moving in that direction? Yes, no. The answer is very simple. Yes or no. How many of you think it's, yeah, it's going to move that way? Or you don't care? That's another answer too, actually. Yeah. Okay, so how about here? Oh, actually, it may, right? Because now we have this. It may. You're right. You get confused, of course. Okay, right. But I'll conveniently say this is going to be ignorable because this is light and this is going to small. So later I will say just this will be the 1D problem. Okay. All right. So in Y direction, basically major action is happening in Y direction. Okay. So the equation of motion is basically F is equal to ma. Ma is total mass times acceleration, right? Okay. And this, oh, I'm flipping the equation, sorry. Okay. This side is inertial force, and the external force we have here is weight of the link, weight of the caterpillar, friction forces in Y direction, and tension force, right? Good. Okay. This equation makes sense to you? Good. All right. Okay. And as you can see, this is minus, this is minus, this is minus. So hopefully our friction force is bigger than this and this and this so that we can have acceleration. Good. All right. Okay. But, you know, we are engineers. First step, we usually want to super simplify this problem, right? Okay. When we saw that video, that robot, do you think it was moving fast, accelerating? The first video we saw was, you know, moving up gradually. Should we say it was moving at constant speed, accelerating, decelerating? How do you think? Constant speed, right? Right? So no acceleration, great. No acceleration means this is 0. So that means this side is 0, right? Okay. Right, so constant velocity, acceleration is 0. Okay, so we can simplify this equation as this, and this is called equation of equilibrium, right? Right? Okay, good. So it's moving, it's still moving. Okay, so feels like that will give us an impression that this is a dynamics problem. But since we all agree the acceleration can be viewed as 0 because of the constant velocity, then we can simplify this problem as statics problem, right? Good. Okay. All right. Okay. And the other thing is rotational case. Okay, we have to satisfy the equation of equilibrium of the rotation. So we can set up that way. Okay. But as you can see, that robot was not even trying to rotate. So we can say these two parts are very small. Okay, very small. So we can ignore this and we can ignore this. So we can just stick to this. Okay. All right. So this is the equation we need to worry about when we are designing this kind of robot, right? Good. Okay, and then next step is finally statics is done, dynamics is done, free body diagram is done. Then we can find out the relationship of all the forces. Then finally we can talk about the strengths of material. That means what kind of force or deformation is happening at each small element. Okay, so let's see what will happen. Okay, all right. If you look at this caterpillar, I said, let's assume this belt has certain thickness, okay? Elastic, viscoelastic, okay? And on this caterpillar part, we have a weight. Okay, I should remove the W, sorry. And tension should be 1 force. Okay, and on this one, we have a friction, right? Good? All right, can you see that? Okay, I'm enlarging this part to here. Good? Okay, and when things starts moving, this rectangular element will not stay this way, right? Right? After I switch on, it's going to rotate and rotate. This one try to rotate, and there will be friction happening here. So what will happen to this rectangular shape? What will happen to that rectangular shape? Anybody? Are you with me? This. Is that okay? Good. And assume there is no slipping happening. Okay. So this is going to rotate. Okay. And but here's a friction. Good. Okay. So what will happen to this guy? Slow down. This side wants to go down, right? Okay, because this is caterpillar, it's going to rotate. But here's friction pushing up. This side wants to go down. So what will happen to this rectangle? Change the shape, right? Right? Good? Okay, good. So that's it, right? So then after we switch on, what will happen is, okay, right? What will happen is because of this force here and force here, it will be twisted, okay? And this is called shear, right? Shear. Good? Okay, shear deformation, shear stress, it will, of course, this friction force is applied entire span. So this has to be somehow converted into small force applied here. Same thing will happen here. Because of that, small force here is called stress. Then you would twist it, right? Good? Okay, and that is the shear stress. Okay, most material do not mind compression, okay, or tension, okay. Right, here's my iPhone, okay. I can push it, it will not break. I can pull it, it's really hard, okay. But if I try to grab this end, one hand go down, one hand goes up, apply the shear, it breaks really easily, okay, because of the shear. Another example is, paper, very simple paper. Good. If you pull, it's very hard to break, right? But if I apply a shear, it's very easy to break. Good. So all material usually hates shear stress. Okay, they don't mind the compression or tension force. Okay. All right. So that's why now finally we got down to the small element level and we are talking about the stresses. Good. And because of this concept here, you know, the small force applied on the small finite element, and what would try to find out what will happen to that element is called strength of material, right? 材料力学. That's the idea. Good? Okay. All right. Good. Okay. Okay, here we go. Then a little bit of the finite element. Oh no, sorry, strength of material. Okay. Let's say this is my shoes. Good. Okay. I live in Tansui. Okay. I commute by metro every day. Okay. I did that when I was in Japan too. Okay. In Japan, trains are usually very packed. Good. Okay. Have you ever been to Tokyo and ride those commuter train before? Okay, very much like a metro, JU in here, but the JU in here, it will not be that packed, right? In Tokyo, it will be packed like twice as much, okay? So once you ride in a packed train, you don't know who will step on you. Okay, that happens a lot. Good. So let's say yesterday I was riding a train, a guy, huge guy, 150 kilograms stepped on me. Case one. Good. Right. And on the way back, lovely lady, 45 kg stepped on me. Good. All right. So if I tell you these two cases, how do you think? Which case I was hurt more? This case hurt more. This case hurt more. Your guess, your guess. This part is sort of funny joke. Good one. Good one, indeed. That's right, right? So, but most people will say, oh, 150 kilogram guy stepped on you. So I must have hurt more in this case. Most people will think that way, right? But if I say, actually, the guy was wearing a sneaker, but lovely lady was wearing the very pointy high heel, then answer is completely different, right? Right? I think everybody will agree with me. This case will hurt a lot. Right? Why? Because the stress is different, right? Okay, 150 kg divided by this entire area, suddenly each area has smaller stress, but 45 kg divided by this tiny, tiny area, suddenly the stress is very high, right? Of course, if you step on me, my foot, this part doesn't hurt, this part doesn't hurt, but this part will hurt very much. Good? All right. On the other hand, this case, step on me, my foot will feel something, but no cell on my foot will be hurt. Good? So this is the sort of, I don't know, I hope it's a good example representing the different stresses. Good? Okay. All right. So that's why instead of just looking at the shear number, macroscopic number applied to the material, okay, we cannot just decide what will happen to the material just by looking at this macroscopic big number forces. Okay, instead we need to look at the microscopic element. Okay, that means applied force divided by area. Applied force divided by area, and that is usually called stress, right? Okay, all right. So if we have a cylinder bar subjected to the force, then idea is we would like to look at each element, small element here, and see what kind of force is subjected to this element, right? Okay, in this case, uniform force is applied, then we can say this element is subjected to a sigma. Usually we use sigma to calculate the tension or compressional force. Okay, and sigma is clearly applied force divided by cross-sectional area, right? Good. Okay, and the shear force. Okay, shear force is shear force is usually, of course, shear force divided by area. Okay, but when we sketch the free body diagram of the element, we cannot just put the force here and the force here. Okay. If we do so, this element is going to rotate. Okay, that means the element here is not rotating. That means same shear is happening here, this way, this side, we should have a shear coming down this way. And these four equals shear stress will twist the rectangle or square element into this trapezoidal shape. Good. Parallelogram, sorry, parallelogram shape. Good. Okay, so basically that's it for today. I think that's good enough. And before I let you go, I would like to, I can skip this part. Okay, right, here's homework. Good. All right, fun part. It's nice to be able to use the brain. Okay, let's say we are going to design this robot. Okay, this is soft hand shape. Good. Okay, so this will do this, and this is actuator. So when the actuator is on, it will push it. So when this bar is pushing it, it will open up. Good. Right. Then contraction will pull. So this case is extended. So clearly unlocked. This one actuator is pulled, so it's closed, is locked. Good. All right. And two elements shouldn't move independently, should be connected. So if we do so and put another actuator here, then once this is stage one is locked, it's not going to move. Then this is unlocked, and activate this main actuator, we can pull this one upright. Right? Can you see it? Good. All right. Then this element has main actuator. Okay, is trying to bring two hands robot closer or away. Okay. All right. Okay. I'll be honest with you. I'm not a robotics guy, so this picture may not make sense to any of you. Okay. If so, my apology. Okay. All right. And we have another actuator here. Okay, this actuator is going to elongate or contract the bar to open this hand or close the hand. Good. And clearly when this is closed, this end is touching the tube, so it's locked. Okay. When the actuator is extending this bar, hand is completely open up or mouth is open. Because of that, this end, this end, this end is not touching, so it's unlocked. Make sense? Okay. All right. Good. Okay. All right. So in this case, this is locked. This is going to activate. This is going to pull up. Good. Okay. Then once that's done, okay, when this moves up, close it, lock it, unlock it, push it, right? Make sense? I hope this will work. Good? Any questions? Okay, you can picture here's a link here, and outside of the link is soft polymers. Of course, we can have the polymer here and here and here. That's good enough. We don't need to cover the entire link using the polymer. Any questions? Does this make sense to you? Okay, all right. So here's the homework. Okay, all right. Let's focus on this case. Top is locked. This is unlocked. This entire system is moving up. Good. All right. This is locked. Okay. So this shouldn't move. Okay. And this bar is pulled inward by the actuator. Okay. All right. And let's say this entire space, this jig here is weight W. Good. Okay. Then I would like to find out for this state to work out, meaning this is perfectly locked, not going to slide, stay there so that we can put this on up. Okay. What kind of actuator force we have to apply here? So what kind of force we have to apply to this bar to pull this down, and this bar should be pulled upward. Okay. I call that one as actuator force. Good. Are you with me? All right. So homework, first one, okay, just look at this one, okay? And I want you to sketch the free body diagram, okay? Partially done, okay? Upper finger, lower finger, good? Okay, I'm breaking this away, okay? And of course I can put this one in the center too, okay? All right, and let's say this, because this entire weight is W, so super simplified, half of the W is carried by this finger, half of the W is carried by this finger, good? Okay, rigorously speaking cannot be right, but it's okay, we are simplified in the problem. And actuator here is pulling in, so this finger is pulled down by actuator force, this finger is pulled up by actuator force, good? Okay, all right, and for the simplicity, why don't we assume this is same actuator force? All right, so what I want you to do is complete the free body diagram, okay? What I can tell you is there's a hinge, right? Hinge, good? Okay, hinge together. So this picture, hinge force is missing, okay? All right, and also this end and this end and this end is touching the tube, yet it's not sliding down. So that means there must be a friction force here, okay? All right, and when you have a tube like this, when you close it, this end is going to push the wall, right? Good. This not touching, so no force. But when it's going to close it, touch the wall, there will be a normal force here, normal force here, normal force here. Good? Make sense? Are you with me? Okay, so this picture, one normal force is missing, friction force is missing, one normal force is missing, friction force is missing, same here. And here I don't have a normal force, friction force, because this is hinged to this guy. So that's why you have a hinge force here. Good? Happy? Okay, so you finish this free body diagram. Then once that's done, you can set up equation of motion, okay? Equation of motion for this one and this one. And since this is 2D problem means potentially this can move in X direction, Y direction, and we need to worry about the rotation around the Z axis. So for each of them, we should be able to set up one equation, two equation, three equation, one equation, two equation, three equations. Good? And even this, well, actually this part is not moving, so this is a pure statics problem. So without worrying about anything, acceleration, we can say 0, 0, 0. Good? Are you with me? Okay, so complete this free body diagram. Okay, then use this free body diagram, set up 3 equations here, 3 equation total, we will get 6 equations. Solving 6 equations simultaneously, I want you to find out what is FAC. Happy? Good? That's the homework. Okay? All right. And what I want you to do is do it on a sheet of paper. Okay? Or if you want to write down everything on your iPad and send me the e-copy, that's okay too. All right, so this is the homework from today. This can keep you a little bit busy. Yeah, but just a couple hours, okay? All right, okay. All right, thank you so much. And yeah, all right, any questions? Yes. I was thinking about Monday, but it's okay, it's a summer school, so yeah, let's shoot for Monday. Good? And worst case, if you need a couple more days, we can say next Friday or so. That's okay. And you are more than welcome. Oh, okay, okay. Oh, okay. So it's a good idea to finish it by next Monday. Tuesday. Okay. All right. So here we go. By Tuesday. Okay. So, but my recommendation is today is Friday, so you go out and have fun. Wake up early tomorrow morning, right? Then finish it. Then you don't need to worry about it. Good? All right. Thanks for coming. Okay. And yeah, that's it. Okay. 停止分享. Good. All right.